Okay, we have a special intro today. This is the only time we'll be using this intro because I need to pay for something. However, we have an extra special intro just for this momentous occasion. Okay, we are now live. Ladies and gentlemen, boys and girls, welcome to the stream. It's a wonderful June 20th, 2018. It's a Wednesday. And it's everyone's favorite time of day, which is where we learn a little bit more about computer engineering and computer science related topics. Now, if you guys, we're live. Listen, just because people are just not showing up, we're going to run through, I tested this out just a little bit ago, we're going to run through the extra special intro today. This is extra special. This is a one-time only thing. Tell your friends. Are you guys ready? Here we go. This is an exclusive just for you guys. Got the NPR morning edition. He said this is the evening edition. Computer engineering live stream. And we're gonna have a lot of fun. Okay, my friends, we're here. We're back. Let's go ahead and get started. If this is your first time on the stream, welcome. I'm Engineering Today. I'm glad that you're here. It's a wonderful Wednesday, and we're going to be learning about computer networks today. I finally have everything set up. I have all my chats open. I've got all of my stream related things open. I finally figured out how to fix the donations on Linux and stuff. Listen, I want to lay this out for you guys up front. You're not obligated to donate. You don't need to donate. The entire point of this stream is for you guys to learn something. There will never be any paywalls. This is all purely for your guys' enjoyment. Now below you'll see a link to YouTube, and you'll see a link to a link to Twitter. If you like the content, why don't you go there as well? The YouTube's going to have all my VODs from Twitch on it. And on Twitter, occasionally I'll give some updates. But enough of that. We're here for the fun and exciting world of computer networks. Now this is going to be a lot of fun. I've never taken a computer networks class, so we're going to learn this together. I think it's going to be interesting. So we can go ahead and go to the start of this book. The first chapter, I think it's page 33. Yeah, computer networks, a systems approach. Let's go ahead and let's get zoomed in. Yeah. So the goal is to make as close to an NPR stream as we can. We'll just gradually name all of the different programs we're going to do after NPR shows. We're going to have one after Wait, Wait, Don't Tell Me, one after Morning Edition. We'll even have a car talk one. Okay. So let's start a foundation. So foundationally, what are we going to talk about when we talk about computer networks? Let's zoom in so we can see a little better. So, suppose we want to build a computer network. One that has the potential to grow, so here we're talking about scalability, and to support applications as diverse as teleconferencing, video on demand, e-commerce, so this is going to be transactions, so something like Amazon, distributed computing, and digital libraries. So we see the two main things that we're going to focus on in this book, which is this idea of scalability. We want something that works, in our models, but we want something that if our models grow, if we need to create some worldwide network, we can still do that with our initial setup. And secondly, we want to support a lot of different things. Typically when we design a network, or when we design anything, we want to make it very general. So if we think about a CPU isn't like a 4-function calculator. A 4-function calculator can only do those 4 functions. A CPU can run arbitrary programs. So that's what we mean by being able to run these diverse applications. Okay, so let's see. So before any of this, before we can get into the guts of what it takes to build a network, we should agree on exactly what a computer network is. So definitions are always good. As long as we have consistent definitions, everybody knows what we're talking about. So at one time, the term network meant the set of serial lines used to attach dumb terminals to mainframe computers. So here we have this idea of master and slave components. So we have something that drives all the control, and then something that simply receives inputs. The main thing these networks have in common are that they are specialized to handle one particular kind of data. So they can only handle one specific format. So like we already saw up here, this isn't going to be great if we have teleconferencing and video on demand and e-commerce traffic. If we have a lot of different traffic, we see that this actually isn't going to be something great. Engineering Today, Systems Approach and Top-Down Approach are the most popular books, I think. Any reason you prefer this one? Or is it just the one you used yourself? So Dash, I actually haven't taken a computer networks class before. However, I know that the computer networks class at my university uses this. And I'm going to be taking the computer network section of the qualifying exam for my PhD in the fall. So I figured I probably should, brush up on the book. Okay, so let's move on. So we talked about older original networks that supported a single kind of data. So these would either be keystrokes, voice, or video. Now one of these, not all three. And they typically connect to special purpose devices. So we have terminals, hand receivers, and television sets. So if we send video, that video is only going to be picked up by a television set. The television set isn't going to pick up things such as keystrokes if you try to send a keystroke. Do you prefer questions in Streams chat or in Twitch chat? Listen, it doesn't matter to me. I have both chats open side by side. I'll scan both of them equally. All right, so let's keep going. So what distinguishes a computer network from these other types of networks? So what's different about a computer network that we want to be scalable and take different types of data than these single-purpose networks? And so this is what we were talking about earlier. It's this generality. We want something that's able to be able to handle many different types of loads that we put onto it. So computer networks are built primarily for general-purpose programmable hardware, and they're not optimized for a particular application. So we have a network, we send bits over it. However, our video that's getting transmitted is not going to transmit better than keystrokes. We're treating this as a bits are bits kind of scenario. So bits are just ones and zeros. It doesn't matter if they represent video. It doesn't matter if they represent keystrokes. They're still just ones and zeros. Okay, so let's see. Today's computer networks are increasingly taking over the functions previously performed by single-use networks. So this idea of generality is becoming so popular that these dedicated channels are now becoming multi-purpose. So once we understand the requirements, how do we proceed? Fortunately, we will not be building the first network. Others, most notably the community of researchers, so this is just saying that we're not going to design computer networks starting from 100 years ago. We're going to take a little bit smarter of an approach, and we're going to build on their foundations. So we're going to utilize this wealth of experience to guide our design, but we're not necessarily having to reverse engineer and reinvent the wheel. So this experience is embodied in a network architecture that identifies the available hardware and software components and shows how they can be arranged to form a complete network system. Very cool. Okay. In addition to understanding how networks are built, it's important to understand how they're operated and managed. So not only do we want to build a network, we want to make sure that we can control what happens on this network. And so this includes for homes, offices, and even cars. Our cars are increasingly becoming connected to the internet, which for a lot of people, they're wondering about the security implications of this. What if somebody can, say, hack your car or maybe get information about the GPS from your car? That's a very interesting problem. And so we're going to look at this from the perspective of the people that build these networks, the people that operate these networks, and then the people that make the applications that interact with these networks. Okay. So let's talk about applications. These are going to be the things that are running that are actually doing things with the network. IoT, absolutely. You know what the biggest joke is with IoT? It's actually, there's an entire field that's a joke, and it's called IoT security. Because the joke is that it's completely unsecure. So many corners have been cut in the sake of devices everywhere. None of these devices are secure. People have found ways to hack Nests. People have found ways. So Nests are they're like the all-in-one thermostat smart home control systems that were released a while ago. Those have been proven to be incredibly insecure. Now they've patched them and they've gotten better, but oh yeah, Dash, that's a joke. For IoT, the S in IoT stands for security. Absolutely. Because there is no S in IoT. There is no security in IoT. Okay, so let's continue on and talk about the applications or the things that use computer networks. So typically, the most common network we're familiar with is going to be something like the internet. That's a pretty funny Twitter link. Your move. That's a pretty funny Twitter link. Okay, so let's continue on. So most people know the internet through its applications. So we know email, we know Facebook, we know Twitch, like the site we're on, we know YouTube, we know Pandora, you name it. We know these applications, but we don't know a lot most of the time about how these applications transmit things from point A to point B. That's a more interesting problem. So that's because we interact with the internet as users. So we're abstracted away from everything that the internet does for us. So internet users represent the largest class of people who interact with the internet. So out of the 7.5 billion people on the planet, most of those people aren't network engineers that are directly interfacing or interacting with how computer networks work. Most of the people, they're users. They're just transmitting data. They're looking at pictures online. They're watching videos. So then there's a subgroup of people, the developers that create the applications. Then there are the operators. These are the people who operate and manage networks. And then finally, there are the architects. So the architects are the people that are actually the ones designing the internet. Or not only the internet's one example. They're designing computer networks in general. The final constituency is a traditional target of networking textbooks such as this one, and will continue to be our main focus. However, throughout this book, we will also consider the perspective of application developers and network operators. So this is an architecture book. It's for network architects. However, even as an architect, we have to be cognizant of who's using these networks and then how these networks will be managed. Okay, so let's talk about classes of applications. So what kind of applications are going to be using these networks? So the World Wide Web, of course, the internet. It's the internet application that catapulted the internet from somewhat obscure tool used by scientists and engineers to the mainstream phenomenon it is today. The web itself has become such a powerful platform that many people confuse it with the internet. So the internet and the World Wide Web, two different things. So we can think of the World Wide Web running on the internet. And it's a bit of a stretch to say that the web is a single application. So once we start getting into these ideas of incredibly distributed systems and incredibly distributed incredibly distributed networks, these definitions become a lot more loose. So in the basic form, the web presents an intuitively simple interface. So users, like you and me, we view pages of text, of graphics, and then we interact with these texts and graphics. We click on them. We do things that, based upon our needs. We want to learn more about something in a page. We'll scroll around. We'll copy things out locally to a text file. We'll play videos. We'll watch videos. So most people are also aware that just under the covers, each selectable object on a page is bound to an identifier for the next page. So this goes more into if you were doing something like writing some HTML, right? So if you're writing some, HTML and you put a picture in there, so a lot of times you'll do a reference in that picture where you'll bind that picture to automatically go to another page that you've already created. Okay. So this identifier is called the Uniform Resource Locator, or URL. So this is the thing at the very top of your browser that tells you exactly where you are on the internet. So that's what that's called, the URL. Okay. So just like this example they give, which is likely a reference for this book, so something that we already pretty much intuitively understand. So this can be broken down even further. So if you're not familiar with using a terminal or a Unix-based operating system, or if you mainly use Windows and use the graphics interface, here's a fairly good way to kind of break this down of how you can start looking at URLs. So URLs, so they provide, let's see, so the string HTTP that you see before pretty much every URL indicates that the hypertext transfer protocol should be used to download the page. So this just specifies a protocol. And then you'll see most web pages nowadays use HTTPS. So HTTPS is, I think, Hypertext Transfer Protocol Secure. I think the S is for security. And so it says that it should look here. So the machine it should look at, or generally server it should look at, is www.cs.princeton.edu. So that's the name of the machine. And then this is the directory on this machine that has the page that you're trying to look at. So we see that, URLs aren't just some mystical, magical thing. We can break them down into something that makes intuitive sense. We're simply opening up a file on some computer. What most web users are not aware of, however, is that by clicking on just one such URL, over a dozen messages may be exchanged over the internet. So one click doesn't equal one message. It can equal a lot of different messages. Let's see. And let's see why this is. And many more than that if the web page is complicated. So if we have a very complicated web page, we're going to send dozens upon dozens of messages. So this message exchange includes up to 6 messages to translate the server name. So just to figure out what this is pointing to, what this machine is, we need, up to 6 messages to turn into an IP address. We need an additional 3 to set up the Transmission Control Protocol, TCP. So a lot of times you may have heard before something called the TCP IP stack, and so that's referring to some of the things that we're going to be talking about in this book, and I think this book it'll have to get into it. So like we said, another 3 messages to set up the Transmission Control Protocol between your browser and the server. So not only do we need to figure out what the internet's name for the server is, we need to connect to the server. So then we add another 4 messages just to send a GET request saying, hey, we want this page, and the server to respond with the requested page. And then there's this other thing we need to talk about, and for each side to acknowledge receipt of a message. So this a lot of times are called ACKs. So an ACK is just ACK. It stands for acknowledge. And then we have something called NACKs, which is exactly the opposite. It's just not acknowledge. And so this makes sure that someone doesn't send a GET. It may never get back to the person that was supposed to receive the page. And then, so let's actually draw this out. This is interesting. So we'll have some computer 1, and then we'll have some server 1 over here. And this will be time. So what will happen? We will send a GET. We need server 1 to send an acknowledge. After this acknowledge, server 1 will then send the page. Scroll down a little bit. Then the computer 1 will send an acknowledge saying, hey, I got the page. And then anything else will likely happen. There's probably some other messages that we're omitting here, but this is the basic idea. The basic idea is that whenever we send a message, generally, we want to receive an acknowledge. There are some messages that do not require ACKs. At least I know in some other transmission protocols there are messages that don't require ACKs. But for most messages, or I think for a lot of messages, we want to make sure that the other side received it. Okay. So not only do we have these simple messages saying we want to get a page and a page was received, this isn't including the millions of messages exchanged by internet nodes throughout the day just to let each other know that they exist. So a lot of times we want to communicate across an entire web network just to make sure that we didn't lose service someplace. Okay. So let's talk about another widespread application. And this is going to be streaming of audio and video. So video on demand, internet radio, these are a lot of common applications that we see online. So while we frequently start at a website to initiate a streaming session, the delivery of audio and video has some important differences from just fetching some web page that's some file. So for example, you often don't want to download an entire video before watching the first scene. So when we play a YouTube video, we don't want to have to wait. If we're watching a 4K video on YouTube, we don't want to wait X amount of time before we're able to watch it. Most people don't have internet that's good enough to do that. And so that's the major difference that we see beyond these beyond the normal web pages. Normal web pages, we want the entire thing to be loaded before we interact with it. So it's how we consume the medium. So note that the difference between streaming applications and the more traditional delivery of a page of text or still images is that humans consume audio and video in a continuous manner, and discontinuity, such as skipped sounds or stalled videos, is not acceptable. So we don't want to have a lot of buffering. Okay, so I think that makes fairly good sense. So let's continue on. So a subtle difference, or a subtle different application, is real-time audio and video. So this is going to be things such as Skype and Google Hangouts and Discord, where we want to be teleconferencing with someone. We want to be, communicating something, and we really care about the latency. And so, like they said, some voice over IP applications such as Skype. So a lot of times this will be abbreviated as VoIP. So when a person on one end gestures, then the action must be displayed on the other end quickly. So these are really latency bound types of applications. So, and when one person tries to interrupt another, the interrupted person needs to hear that as soon as possible. So we don't want someone to be talking for, 10, 15 seconds before someone on the other side says, wait, I didn't understand what you said previously. So contrast this to video on demand, where if it takes several seconds from the time the user starts the video until the first image is displayed, the service still seems satisfactory. So I guess this depends on who you ask. Some people want it to start immediately. However, when we consider it from a more realistic point of view, there isn't going to be some massive miscommunication if the video takes 5 seconds to start versus if someone's talking for 5 seconds and somebody else can't interrupt them for some reason. So let's talk about video conferencing tools that run over the internet. So video conferencing has actually existed since the 90s. I didn't know this. That's a lot older than I would have expected. Okay, an example of one such system is shown in figure 1.1. Just as downloading a web page involves a bit more than meets the eye, so too with video applications. Fitting the video content into a relatively low bandwidth network, so we're talking about an old system, so it's going to have low bandwidth, and we need to make sure that it stays in sync and then it arrives on time. So we don't want a video that arrives all out of order or have any issues depending with how we patch this message back together. And so we'll look at a lot of these issues with multimedia applications later. So let's see if we can find this. Okay, so we have so I guess this is that old communication, video conferencing tool from the 90s. Although this doesn't seem like it's from the 90s. I'm going going to go ahead and say that this is not from the 90s. This is just whatever they had available. Okay. Although they are just two examples, so downloading pages and video conferencing, the diversity of applications that can be built on top of the internet and hint at the complexity of the internet's design. So basically we're saying that, even though we've only gone over two examples, there are many, 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 many things going on in the background that shows that these networks can be very, very complicated. Okay, so let's continue on. So requirements. So now that we've talked about what kind of things are running on these computer networks, we're going to talk about some of the requirements. So we've established the ambitious goal for ourselves. So we want to build a network first from the ground up. And of course, like every good engineer, we need to start at first principles and then ask the kinds of questions we would naturally ask if building an actual network. So we start out with the foundational knowledge, and then we start to ask the practical questions. So at each step, we will use today's protocols to illustrate various design choices. However, we're not going to blindly accept things. So we want to be a little bit smarter if we need something specifically. We want to make sure that we're not saying, okay, well, this isn't supported by this protocol, so we're just going to ignore it. So we need to be a little bit smarter. Okay, so let's talk about perspectives in terms of requirements. So these are the perspectives that we talked about earlier. So from the view of an application programmer, we would list the services that his or her application needs. For example, a guarantee that each message the application sends will be delivered without error within a certain amount of time, or the ability to switch gracefully among different connections to the network as the user moves around. So we can think of this such as like Facebook's Messenger. And so we can break that down here. So let's look at the first guarantee. We want each message the application sends, so all sends must be delivered without error. Now, I don't know how many people here have ever received an incorrect message on Facebook, but I know that I never have, so they clearly got this right. Now, it also says within a certain amount of time. That means we don't want somebody to be responding 3 hours later when 10 messages from 2 hours ago come in. Okay? And then, if we get on different networks, so if I'm at home and I send a message to somebody, I want to still be able to send messages to that person if I say have to go to the airport and fly out and go to a different state. I want to still be able to send messages. So let's see what we want to look at from the perspective of a network operator. So when we're talking about requirements of a network operator, we want the characteristics of a system that is easy to administer and manage. So we want something that we can sufficiently control. So we want to be able to isolate faults. We want to be able to add new things to the network. And we want it to be easy to use. So these aren't necessarily too overly ambitious of goals. All this is saying is that we want to be able to catch errors, we want to be able to add new things to the network, and we want it to be easy to use. So simple goals typically lead to simple designs. A network designer would list the properties of cost-effective design. So for example, that network resources are sufficiently utilized. So if we build a network, we don't want to make it so incredibly complicated for very few users. So let's say if the entirety of Twitch had the audience that, say, I have, say no streamer had more than 13 viewers. Now, in that case, Twitch probably wouldn't want to be storing the data for all the VODs that get recorded. They wouldn't want to be providing the bandwidth to stream at 1080p 60 frames a second or 30 frames a second, or if they can stream in 4K, they probably wouldn't want to support that because it doesn't match the requirement, and they wouldn't effectively use the hardware that they had purchased. So they want some amount of fairness or quality of service. And so we're mainly talking about performance in the terms of a network designer. And so what we really want to do is we want to distill these different perspectives. So we want to make sure that when we're talking about an issue, we know whose problem it is. So let's talk about scalable connectivity. So starting with the obvious, a network must provide connectivity among a set of computers, otherwise it's not a network. Sometimes it is enough to build a limited network that connects only a few select machines. So we want a very close, a very private network. In fact, for reasons of privacy and security, many private corporate networks have the explicit goal of limiting the set of machines that are connected. So at a company that I worked for, this is exactly what we had. We had an internal network where we could access our internal sites and our internal documents. However, if we say went home for the day, unless we actively accessed an entry point into that network, if we were just on a regular network, we wouldn't be able to get in. We wouldn't be able to access those same files. So this is in contrast to other networks, such as the internet, that are massively available. So anybody from anywhere can access this. And they're designed to grow in a way that allows all people, or many people, to connect across the world. And so these are large. So when we're talking about large size, we're generally talking about scale. We're talking about these systems at scale. So let's talk about links, nodes, and clouds. To understand the requirements of connectivity more fully, we need to take a closer look at how computers are connected in a network. Connectivity occurs at many different levels. So at the lowest level, we're talking, one or two computers directly connected, such as by a coax cable or a fiber optic cable. You can even think of this as simple as, you plug your phone into the computer. Those two devices can now communicate. And so we're going to call this a link. So when we talk about physical things, we're talking about linking these together. And we refer to the computers it connects to as nodes. So nodes are connected by these physical links. Okay. So it's illustrated by figure 1.2. So here's 1.2. So we have direct links, which is computer A to computer B. And then we have, so this is point to point. And then we have multiple access direct links, where we still have this link over here. However, we have many nodes now. Okay. And so that's what we say here. We talk about point-to-point and multiple access. So things like wireless and Wi-Fi are examples of multiple access links. But when we're talking about something like Ethernet, we have a single cable that's connecting something to something else. So now we're going to talk about two examples of how collections of computers can be indirectly connected. So this is direct connections over these physical links. So let's talk about indirect. So figure 1.3 shows a set of nodes, each of which is attached to one or more point-to-point links. So we have nodes connected to links, to point-to-point links. These nodes that are attached to at least two links run software that forwards the data received on one link out on another. So now instead of directly connecting two things together, now we have this intermediary that's going to route it to a different link. if organized in a systematic way, and it's very important that we do things systematically, we don't want a lot of individual one-by-one cases that we're looking at. So these forwarding nodes form a switched network. So that means that basically you can think of it as a physical switch where we're connecting between two different networks, or between an arbitrary number of networks. So let's go ahead and look at this picture. So here we go. So here we have this idea where we have two inputs and 3 outputs, say, from this switch. So we have 2 direct links that go into this box that's a switch. Now, within the internals of the switch, it decides which one of these outgoing links it's going to go on. And in this case, they're all going to go to another switch. And then this switch itself is going to decide which link it goes out on to the end machine. And so that's what we mean by indirectly connected. So instead of directly going to another machine, we're going through some cloud medium or some other medium where we have these switches. And so we're talking about circuit switched and packet switched. So circuit switched is generally telephones, and then packet switched is computer networks generally. And so then they make a brief aside here where they say that although this was the case, so originally things were circuit switched, and then computer networks eventually became packet switched. But now when we're talking about fiber optics and optic networks, so now we're moving a little bit more back to circuit switched. So the important feature of packet switched networks is that the nodes, such as a network, so that the nodes in such a network send discrete blocks of data to one another. So discrete blocks to each other. Think of these blocks of data as corresponding to some piece of application data, such as a file, a piece of email, or an image. So this basically says when you send an email, it doesn't come as one big bunch. We turn it into a series of packets that we then send to their final destination. Okay, and these are called packets or messages. Okay. Let's move on. So packet switch networks typically use a strategy called store and forward. As the name suggests, each node in a store and forward network, it gets a complete packet from some link. It stores the packet in memory, and then it eventually forwards the complete packet to the next node. Now, you don't have this, as far as I'm aware, you don't have the same kind of storage in a circuit switch network. So what happens in a circuit switch network, we get a dedicated circuit across a sequence of links. So basically there's this arbitration process where the final result, so let's say we have 3 different boxes. This is my interpretation of this. So say we have a PC here. We have a switch here, and then we have PCs here. In a packet network, we're going to send packets here. It's going to, so let's say this packet wants to go, so let's call this PC A and PC B. So this packet, say we want to go to A. So we'll send this packet and we will go to this switch. Let's say that this packet gets stored here. But let's say at the same time, maybe we're also sending another packet, B. Now, in a packet type network, we're going to put these packets in memory, and then we're going to write them to their correct destinations. Now, when we're talking about a switched network, it's a little bit different. So we're now talking about more physical connections. We're talking about something like a fiber optic connection. So what's going to happen is we want to send, say, message A. What's going to happen is this switch is going to make a connection to this PC, and we're going to have A here. It's going to go through the switch, and then A is going to go on this link. So that's what we mean by the idea of these circuit switch networks and these packet switch networks. Okay. So the cloud in figure 1.3 distinguishes between the nodes on the inside that implement the network. Okay. So they're commonly called switches. So like I said, these would be called switches because they switch between these different links, while this guy has just a single hard link. And the nodes on the outside of the network use the network. They're called hosts. So now we have hosts and we have switches. So you see, we're starting to get some of the jargon and some of the lingo that we hear a lot when we hear about data centers. Yeah. Okay. Also, note that the cloud design in figure 1.3 is one of the most important icons of computer networking. In general, we use the cloud to denote any type of network, whether it is single point to single point, multiple access link, or switch networks. So we're just talking about these multi-access networks that can be single point to point links, multiple access links, or switch networks. And so here we have interconnection networks where we have some other medium in the middle that talks between these banks of switches. So this allows us to create a more scalable design like we were talking about. So we can think of this as a single block of a diagram. And here we paste together 3 of these blocks with a single intermediary. Okay, engineering today, having some trouble following the distinctions between a circuit and a packet. Okay, so you can think of a packet as some organized piece of data. Now we send this in a chunk across this network switch. It gets buffered by this switch. This actually is easier if we say this is, let's call these PCs now C and D, and let's call these PCs A and B. So let's say both PC A and PC B send a packet. So we'll call this packet A, and we'll call this packet B. Now what's going to happen is that these packets will go on the switch. This will be A, and this will be B. The switch will do the routing, and so packet B may go here if it's supposed to go to PCD, and then packet A may go here if it is supposed to go to PCC. Now when we're talking about these dedicated circuits, these circuit switch networks, we physically stop this connection. And so we make it so that the only connection that we have coming out of this switch is this direct connection with, say, PCC. So what's going to happen is we're going to do our data transfer from PC A to PCC through the switch. Then, after we finish the connection, PCC will say, or after the data is finished transferring, PC A will go, I'm done transferring data. This link will be cut. And then we'll do some arbitration, and now we'll make our connection to PCD, where we can start transmitting our packets from B. So basically the difference is in the packet setup, So you're still transmitting things called packets, right? So packets is just a way of formatting data. However, when we talk about something such as, let's see, packet switch networks, all that's saying is that in packet switch networks, we're putting the packets in the switch, and then at the same time or as available, we can just give them to all the machines we're connected to. Now, in a circuit switched, it's a dedicated circuit over here that can connect to a single device and do a high bandwidth transfer. That's the distinction we're making. Single connection versus, less performance, but we can have more access from more machines. Okay. So let's move on. So a second way in which a set of computers can be indirectly connected, as shown in figure 1.4. In this situation, a set of independent networks, so clouds, are interconnected to form an internetwork. So now we're taking this idea of clouds, which are already connections of switches connected to hosts. But now we have this intermediate layer where we can connect these clouds together. Yeah. It's very confusing. So they call it a packet switched, but it's important to realize that packet is also what we call the data being transferred. So data is transferred in things called packets. So we adopt the internet's convention of referring to a generic internet work of networks as the lowercase I internet. And the currently operational TCP/IP internet is the capital I internet. So now we have two different internets that we have to worry about. Oh joy. A node that is connected to two or more networks is called a router or a gateway. So these are going to be routers. We got some, I don't know where this guy came from. Doesn't want to go away either. Okay. Well, more power to him. Okay. And it plays much the same role of a switch. So now we have basically switches of larger scale. We have switches between these links that go between hosts. And now we have switches that go between, or switches that we're now going to call routers or gateways. That connects different networks together. Okay. Interesting. So let's say just because a set of hosts are directly or indirectly connected to each other does not mean we have succeeded to provide host-to-host connectivity. So just because we've connected lots of things together doesn't mean that someone can get from point A to point B. The final requirement is that each node must be able to say which of the other nodes on the network it wants to communicate. So we need to know, just like addresses have the name address for a reason. So just like, a home or a business has an address, computers have an address for the same reason, which is they need to be able to figure out where someone else is located. And so now we're going to talk about assigning addresses to nodes. And so, like we said, an address identifies a node, and networks use this node's address to distinguish it from other nodes. So two people generally don't have the same address. So if someone lives at 123 Canyon Lane, there typically aren't two houses at 123 Canyon Lane. Okay. So when a source node wants a network to deliver a message to a certain destination node, it has to specify the address of the destination node. We can't just say, here, I want you to send this packet. Because if we don't say, send this packet to Bill's house, then it won't know where to go, of course. And so the systematic way, or what we call the systematic way of forwarding messages, is going to be called routing. And this is based upon addresses. or addresses. This brief introduction to addressing and routing has presumed that the source node wants to send a message to a single destination. So sometimes we want to broadcast a message. And that's what we say here. We want to broadcast a message. And so that's in a situation that we call multicast. Okay. So now that we've talked about, a little bit about specifying the requirements of networks, we can start to bring in things such as cost. So whenever we bring in cost, we start to bring in ideas of practicality. So as stated above, this book focuses on packet switch networks. This section explains the key requirement of computer networks, which is of course efficiency. We want efficient networks because we want a fast internet. Given a collection of nodes indirectly connected by a nesting of networks, it is possible for any two hosts to send messages to each other across a sequence of links and nodes. So just to go over some of this terminology again, when we're talking about hosts, we're talking about PCs. When we're talking about links, we're talking about the connections to switches. And when we're talking, sometimes nodes and switches are the same thing. And then these in big systems connect via routers to one another. Of course, we want to do more than support just one pair of communicating hosts. We want many people to be able to talk at one time. The question then is, how do all the hosts that want to communicate share the network, especially if they want to use it at the same time? And, as if that problem isn't hard enough, how do several hosts share the same link? So if we want multiple people to use the same physical hardware, how do we do that? And so a lot of times we call that multiplexing, or time division multiplexing. This basically says that we split our time up, so we'll have a block of time. So this will be time. And we'll split this up. And let's say we split it up 4 ways. And we'll say process A gets this block, B gets this block, C gets this block, and then maybe we loop back around to A. So that's what we mean by time division multiplexing. Everyone gets their own slice of time. Okay. To see how this might work, consider a simple network illustrated in figure 1.5. Okay. So if we have a single pathway to go across this physical link between 2 switches, but we have 3 computers, we can't use this single link 3 ways. So what happens is we have to do a little bit of buffering right here, which means that we have to say, okay, S1 and S2 maybe sent their commands later than S3. So S3 sent first. So we go, okay, first S3 makes a connection and begins transferring data. Now S2 comes along, and S2 hits this point, and it gets blocked because somebody else has this link. And then S1 comes along, and somebody else has this link. Now, let's say this guy has had it for some amount of time. Eventually, we'll go, okay, well, we got to play nice. We'll cut this guy off and say, you can finish transferring later. And then we'll say, okay, well, system 2, host 2, you can now go, and you have access on this link. And then that will continue on, and it'll continue on over and over and over again until, everyone has a short amount of time in the link, and then it will go just in circles and circles. So that's a very intuitive but, kind of a naive way to do it if we just kind of go around in a circle. But maybe that's good enough sometimes. So that's more time division multiplexing. So then they also bring up the idea of frequency division multiplexing. So I'm actually not sure what this is. The idea of FDM is to transmit each flow over the physical link at a different frequency. Okay. So this is a way of communicating many things together over the same link, but just telling them, okay, so process A, you have some frequency. So this we have S0, S1, or S1, S2, S3. So S1, you get assigned to, say, frequency 0. S2, you get assigned to frequency 1. S3, you get assigned to frequency 2. And then these are all combined into, say, some frequency N. And this is communicated over that link at one time. And then it's decoded on the other side. Okay, that's a very interesting concept. And so this is the same way that TV stations are transmitted at different frequencies over the airways or on a coax cable. So, although it's simple to understand time division multiplexing and frequency division multiplexing, they're both limited in two ways. So first, if one of the flows, so host pairs, does not have any data to send, its share of the physical link, that is, its time quantum or its frequency, will remain idle. So this basically says, if we're going between, in some timed order, between A, B, C, A, what if A, for example, is always 0? What if A is always 0? That means we're doing no work here. B and C chug along, and then we're doing no work again. So we're wasting half of our time here. Okay, so that's what we talked about first. So no data. Let's see. Where do we go next? Let's talk about second. They are limited to situations in which the maximum number of flows is fixed. So this says if we want to communicate between 3 machines, everyone gets, say if we have little bursts of 6 seconds, everybody gets 2 seconds of time. Now this means that at most we can have 3 machines because everyone's supposed to get 2 seconds. But if we wanted in machines, or if we wanted, even if we took a real number, so say 10 machines or 11 machines, our system no longer works. So it's not practical. So the form of multiplexing that addresses these shortcomings is called statistical multiplexing. So although the name is not helpful in understanding what it does, the concept is quite simple. So like time division multiplexing, we have all the physical links shared over time. So first, data from one flow is transmitted over the link, then from another, and so on. However, the data is transmitted from each flow on demand rather than in predetermined time slots. So this basically means that if system A or system 1 wants to send something, it puts a request on the switch and it goes forward. Then system 3 puts a request on the switch, it goes forward. System 2 puts a request on the switch, then it goes forward. The only important thing there is we have to make sure that nobody necessarily hogs their time on the switch. Okay, so as defined so far, statistical multiplexing has no mechanism to ensure that all flows will eventually get the term to transmit over the physical link. So if we say that we do something on demand, this doesn't say that we will kick someone off at some point. So then they go into this limited size block of data, typically referred to as a packet. And basically what we say is we'll cap the amount of packets that somebody can send. That way everybody has their time to send some packets. And so in this case, we have things called messages that are comprised of packets. And we need ways of being able to split messages into multiple packets or fragment them. But we also need a way, of course, for the receiver, wherever we're sending these packets, to be able to reassemble them. So in other words, each flow sends a sequence of packets over the physical link with the decision made on a packet-by-packet basis. So this is important. It's on packet-by-packet basis as to which flow's packet to send next. So here we have an example. So now we have packets coming in instead of people taking direct control of the network. These packets get queued, say, one at a time. So say first S1 puts a packet in. It has its turn. So this is from S1. Then we have these lighter packets. So S2. Then we have these, let me remove the highlighting real quick. So this was probably S3, then this was S2, then this was S1, and then we roll around again and we're back at S3, and then this time we go S1. Age of the Rage. Wow, I feel like I'm in my operating system class again. Multiplex time memes. Hey Idra, I have a question for you. In your operating systems class, did you talk about time multiplexing when you were doing process schedulers? That's what most people, I think, do. When they're talking about like real-time schedulers and the fair scheduler. Yeah, I know exactly what you're talking about. So I took an operating systems class that we hacked the Linux kernel in the class, and we had to design our own Linux process scheduler based upon the completely fair scheduler that's implemented in the Linux kernel. I don't know if you might have had to do something similar. I think that's a fairly common project. I know Columbia has to do that project, the Columbia operating systems courses. Okay. So let's move on. So the biggest takeaway that we're going to take from this big block of text right here is this idea of quality of service. So while we could implement something that's very low hardware cost that does something very simple, such as time slice a link so that everyone gets an equal amount of time on the link, we don't necessarily ensure that we're not wasting time or that we're not limiting somebody's bandwidth too much. And so this brings up this idea of quality of service, or QoS. And so QoS is something that relates to more than just network packets. So for me, as an architect, a lot of times in GPUs, what we're concerned about is when we're sharing GPUs, say in a cloud environment, we want to make sure that somebody can't send a ton of memory requests that's going to, soak up all the memory channels of the system and make it so that when I do a memory request, I get serviced last. So this is this idea of QoS, or fairness. Okay, so let's move on. Also, notice in figure 1.6, okay, so here we have this multiplexing going into a single line of packets. So that means these three systems are all sending information to one system. Okay, so what do we have next? So we can go over this brief aside about SANs, LANs, MANs, and WANs. Isn't that neat? We get all these cool little acronyms that we get to learn. So two common two common types of networks are local area network, LANs, and wide area network, WANs. So when we're talking about local area networks, these are generally small networks, less than a kilometer, while WANs can be something that's worldwide. So there's other classifications, so MANs, or metropolitan area networks. So these can be tens of kilometers, so slightly bigger than a LAN, but they can be, or usually are, significantly smaller than a WAN. And so, this may seem arbitrary. Why are we talking about networks in terms of their size in kilometers? This may seem silly to us. However, a lot of times when it's important for us to make distinctions between different levels of size. So if we're talking about the memory required by some tiny microcontroller in some IoT scenario, it's convenient for us to talk about caches at or memory size, maybe in the kilobytes, maybe in the megabyte range. However, if we're talking about some giant PC or maybe a graphics card or something in a giant server scale system, we want gigabytes or terabytes of storage. So this is all this is doing. It's just giving us different ways to describe different sizes. Okay, now support for common services. So the previous section outlined the challenges involved in providing cost-effective connectivity among a group of hosts. But it is overly simplistic to view a computer network as simply delivering packets among a collection of computers. So we can't just, abstract away a lot of the nitty-gritty details. We need to make sure that we're talking about every part of what's going on when we transfer a packet. So it's better for us to think of this as providing the means for a set of application processes that are distributed over these computers to communicate. So the next requirement of the network is that the application program running on hosts connected to the network have to be able to communicate in a meaningful way. So that means we can't have everyone talking to a network in an arbitrary way. We need a set way to talk to the network. So how can we talk about this? So intuitively, we can just look at the network as providing logical channels. So a network is just something that has all these openings that we're going to call channels that transmit over specific areas. And so an application level process can communicate with each other over these channels. Okay. So here we have 1.7. So we have some host application over here. It uses some channel in the cloud, so it goes through some nodes and some switches in order to get to some other application that it's talking to. So we can just consider this region in here the channel. The challenge is to recognize what functionality the channels should provide to application programs. For example, does the application require a guarantee that messages sent over the channel are delivered, or is it acceptable if some messages fail to arrive? Is it necessary that some messages arrive at the recipient process in the same order in which they are sent, or does the recipient not care about the order in which messages arrive? So this just really goes into ordering. So when we're talking about, say if we're sending remote commands, we can even do the extreme scenario. Say we're controlling something related to the power grid. If we're doing this remotely, it's probably very, very important that these commands arrive in the order that they are sent. We don't want to, or let's say it's something like say we're controlling a furnace. And say we have 3 commands. We have open the furnace, we have close the furnace, and then we have, say, dump the contents of the furnace. Now, if we didn't have a guarantee that commands would arrive in order, we would perhaps, the first thing we do, some hot furnace, we would say dump the furnace before we even open the furnace, so we may just ruin the furnace if they don't arrive in order. But sometimes it's okay. So let's say email, for example. Email, we want messages to arrive fairly quickly after we send them. However, if 2 emails come in out of order, say if Bob sends an email to me and Sally sends an email to me, if Sally's email comes in first or Bob's email comes in first, it doesn't make too big of a deal. Industrial application examples, yeah. So here's a fun fact about me. I actually, before I started my PhD, I did a little bit of a stint and I worked as a safety engineer, and so I got to tour a lot of production facilities. You missed most of the lesson today? You didn't miss most of the lesson today, Kamikaze Chicken. Listen, we still have plenty of information to go over. That's A-okay. I'm glad you're here now. How's everyone doing today? Is everyone having a wonderful day? Is everyone having a wonderful Wednesday? We're halfway through the week. We're halfway through the week already. I'm having fun here today. I'm glad you're with us. I actually spent a lot of today, building up some brand recognition. I went around, posting ads on Reddit saying that I was going to be doing some teaching streams. Pretty cool. I'm going for a BS in mechanical engineering, so the industrial examples can be a refreshing bit of familiarity. Yeah, so, that's an interesting thought. So most of the times we can relate anything that's in an electrical environment to something physical, right? So when we talk about switches in the cloud, those can be directly related to, physical switches. Just because if we were to implement them in reality, they would be very, very much abstracted away from physical switches, doesn't mean that the physical nature of them isn't any less true. Okay. Feeling good today. Well, that's great. I'm glad you're feeling good today. So let's talk about identifying common patterns. So one of the earliest applications supported on any network is a file access program called FTP, so File Transfer Protocol, or NFS, Network File System. So details vary from example to example. However, it's important that we just understand that, we have specific protocols that communications talk to the network in, but they talk to the network in set ways. They don't talk to it in variable ways. So, in one example, reading a file involves the client sending a small request message, the server responding with a large message that contains the data in the file, and then the opposite true is for writing. So we see that we don't necessarily say we don't ask for some part of the file before we send a message to say open the file. A digital library is a more sophisticated application than file transfer, but it requires similar connection services. For example, ACM, the Association for Computing Machinery, operates a large digital library of computer science literature. So I get most of my research papers from ACM, actually. Okay, so this is basically, most of these examples are going over is just the idea that we need to talk with networks in very set ways and set fashions. Let's see. Okay, and that's all we're saying here as well. Also note, so over here I think we're talking about something that is a good note to understand, is that also note that independent from what functionality a given channel provides, there's the question of where that functionality is implemented. So is it going to be implemented on the host side? Is it going to be implemented on the switch side? Who's going to do this? So in many cases, it's easiest to view the host-to-host connectivity of the underlying network as simply providing a bit pipe. So a lot of times we just want to think of this as, okay, here's some, this channel is literally just a channel. You can send anything you want and it will just flow through this channel. And then we'll have kind of hidden layers in there that will do all the complicated things, such as structuring messages for us. Okay, so let's talk about reliability. So it's very important for us that, like a series of tubes, yeah, pretty much. So a lot of times when we send a message, so let's take Facebook, for example, correct? Or let's take anything where we are. Oh, I've got a great example. So let's say if you're on a command line and you're just doing ping, you're just pinging a server, okay? So when you ping a server, what you're actually doing is you are creating a packet. That packet is being sent over a channel to someplace else. Maybe it's being sent to Google. And then Google is responding in kind with the packet. However, from the interface of the terminal, you're just writing ping. You are not structuring a packet. You're not looking at what's involved in creating that packet and then sending that packet over the network. You are just saying, send some data. Okay, so now let's talk about reliability. Reliability is another very interesting concern. So the first thing we have to recognize is that the world isn't perfect. So they don't exist in a perfect world, and that machines crash, but we want to be able to recover from crashes. So there's 3 general classes of failure that we have to worry about. So we have bit errors in the data. So this is when some crosstalk, some coupling occurs when we're transferring data, or maybe there's some fluctuation of power and then maybe a 1 flips to a 0, or maybe a 0 flips to a 1. So the data on the other side is incorrect. Sometimes single bits are corrupted, but more often type of error is burst error, where we have a group of bits that are now corrupted. And so these are caused by a little more coarse-grained problems. So lightning strikes, power surges, ovens, or microwaves rather. Okay, some interesting examples here. The good news is that such bit errors are fairly rare. So they only have an effect on, so this is 1 million bits or every 10 million bits on a copper cable, and then on a fiber optic cable, much more. So this is million, then it would be billion, then it would be trillion. So this would be every trillion bits or every 100 trillion bits. There would be an error. It's a lot like DNA mutation. Whoa, dude. Yeah, man. It's a lot like DNA mutation. So we have some little influencing force that causes some bits to flip. And we'll also see that just because some bits flip doesn't mean we can't recover from it. So we do have some recovery mechanisms. Oftentimes we call things like this ECCs, or error correcting codes. And this is something that we build into the transmission protocol. And I actually have I've got some secret slides that we can go over sometime from a presentation that I was a part of. Okay, so what's the second class of failure? So these are bit level failures. The second class is at the packet level. So rather than something going wrong with the bit, we lose a packet. So how do we recover from this? So oftentimes this happens because something happens at a node and it can't handle a packet, and then it gets lost someplace. So say maybe memory's full of wherever it's communicating, and so because it's full, maybe it can't at that point, recover. It just says, okay, I can't store this packet, send it away. Just send it away for now. Less commonly, the software running on one of the nodes that handles the packet makes a mistake. So most of the time, software being written for things like packet management is very, very good. It has to be, or nobody would use it because they would get so many errors. And so then we have a third class of failure, which is at the node or the link level. So this is if we have a problem where we have an Ethernet cable that goes out, or we have a router that goes bad. So that's this third class of failure. So this is more extreme. So something like a bit level failure is something that we experience, however, this is usually hidden by the system with all the fandangled fancy ways of doing error correction. So we normally don't even interact with this. The second class, we lose packets. We typically see this when we complain about our internet being bad. Oftentimes when our internet is bad, we see a lot of packet loss. And then the third class, this is when we, maybe completely lose connectivity with something, or say a site on the internet goes down, or maybe something's wrong with our Ethernet cable. Okay, let's see. So let's talk about manageability. So when we have a network like this, we want to be able to manage it, of course. Because, of course, if we build something, we need to control it. So this requirement is partly related to the issue of scalability. So we don't want to have something that we build up to be everywhere that gets out of hand. I like that the classes of failure are structured in the same way as degrees of burns. Yeah, absolutely. Yeah, it's pretty funny. So now that we're at the scale where we're supporting billions of devices and at least hundreds of millions of hosts, the challenges of keeping the whole thing running correctly and correctly configuring new devices as they are added has become increasingly problematic. So I think one of the biggest problems that was recently had to be addressed was the IPv4. So it was the IPv4 address range was not large enough for the number of networks that existed. So that's the reason why IPv6 had to be invented. Now keep in mind, I'm not a network engineer, but I do have a little bit of context into these things. I did work on server related things for a couple years. Okay. So configuring a single router in a network is a task often of a trained expert. Now listen, you guys have to tell me, did you guys get a trained expert when you had to set up a router? Did you get when you buy a router from Amazon and you get the pro installation for $200 more, did you get that? When you say you bought your internet or you bought your router from Amazon, did you guys get the $200 pro installation of your router where you plugged it into the wall? Of course, this is a joke. They're talking about something a little more complicated. You called the head of Cisco? That's probably a bad idea. Because Cisco had that huge insider trading scandal that went around where right before some big security leak came out, like the CEO of Cisco or something sold like all of his shares, and then they said, no, it wasn't insider trading. It wasn't related to this. Yeah, I don't believe you. Does the piece of paper it comes with count as an expert? I think it should. If you're not like the people that just they go, I can't understand the computer, I can understand how it works and just give up immediately. If you're one of the people that can pick up a piece of paper, follow the instructions, and set up a router, listen, you're more tech savvy than I would think half of the people in the United States. Half of the people seem to say, oh, that's just a tech thing. I'm not good with computers. That seems to be a big problem, that people think that they can't do anything. Okay. So let's talk a little bit about network architecture now. So now we're on 1.3. So when we're talking about to deal with the complexity of networks and all these different layers, we want to have general blueprints, usually called network architectures, that guide the design and implementation of networks. So this doesn't mean that we're completely following a build plan that says connect A to B with this wire. It says that we have a good guide to telling us how we should design a network. Reading comprehension, yeah, it's something that people seem to miss nowadays. And so we're also going to introduce two of the most widely referenced architectures, OSI, or 7-layer architecture, and internet architecture. I used to remember OSI. Back when I worked on server stuff, I took a brief corporate training class on OSI, but it's been so long now, and I don't do this kind of work anymore, so I completely forgot. So when we're talking about architectures, it's often good for us to talk about layering and protocols. So when we're talking about protocols, we want to break things down into different layers. So we want to break, first of all, we want a hardware layer to interface with what the hardware is actually doing. We want to break it to host-to-host connectivity. So we want to be able to get from machine to machine. We want to communicate with different process-to-process channels before we get to the hosts. And then we want to have our applications at the highest level that are going to start this process of sending something over a network. And so here we have a layered system with alternate abstractions available at a given layer. So here we have again the application programs. Then we have now two different channels, a dedicated request reply channel, and then we have another one for streaming data. And so generally, if I'm remembering correctly how this works, from the application, so let's call this PC1 and let's call this PC2, what will happen here is that we will say send a request, and we'll call this an R. We'll get an acknowledge, we'll call this an A, and then we'll have a stream of data, and so we'll call this S. And then maybe sometime during in here, at the same time, we might generate another request. So we're parallelizing some of this. And then, of course, we still have the same host-to-host connectivity. And, of course, we have the same hardware. So this just shows we have some flexibility in these layers where we can parallelize some things as we want it or as the scenario demands. So using this discussion of layering as a foundation, we are ready to discuss the architecture of a network more precisely. For starters, the abstract objects that make up the layers of the network are called protocols. That is, a protocol provides a communication service that higher level objects, such as application processes or even higher level protocols, use to exchange messages. So then they give us an example. So imagine a network that supports a request-reply protocol and a message stream protocol. So that's this scenario. Okay, so yeah, that's this. So up here we still have the application that seemingly has the same interface down here, but now we have a different protocol. Each protocol defines two different interfaces. So we have the service interface to other objects on the same computer. And then we also have the peer interface of a protocol to a counterpart or peer on another machine. So we either have communication within the same machine or maybe across machines. So this second interface defines the form and meaning of messages exchanged between protocol peers to implement the communication service. So this determines the way in which request reply protocols on one machine communicates with its peer on another machine. So in the case of HTTP, in the protocol specification, defines how a GET command is formatted, what arguments can be used with the command, and how the web server should respond when it receives a command. So here we have services interface, so that interface is going to be on the same host, and so it's going to be a protocol and some high-level object. And then, of course, we have the peer-to-peer interface, which is going to be between host 1 and host 2, so two hosts. So to summarize, a protocol defines communication. So when we say protocol, you should think communication service. So it defines a communication service that it exports locally, the service interface, as well as non-locally, the peer interface. And so that's what we're talking about here. So service and peer. Except at the hardware level, where peers directly communicate with each other over a link, and peer-to-peer communication is indirect. So each protocol communicates with its peer by passing messages to some lower level protocol, which in turn delivers the message to its peer. So we therefore represent the suite of protocols that make up the network system with a protocol graph. So let's take a look at this before we read any more, or if we read any more. Let's take a look at 11. So here we have two hosts. We have our applications, be they file or digital library applications or some video applications. We have a layer for requests and replies. And so in this case, whenever we have a file or whenever we have some digital library application, we know that we want to request a file and reply maybe with that file. And then on the other side of things, we have a stream. And so generally this is for streaming things. So like you guys are streaming on Twitch right now, it's going through some MSP. So then it goes to the host to host protocol. So how do I get from point A to point B? How does this get from my machine to the networks at Twitch over to your machine? So that's what this is specifying. And then of course, replies and streams work the same way. So we can actually draw this out, right? So we'll call this Twitch, and we'll say this is me and this is you. So what you guys do is you send a request across this streaming. It goes here, this host to host protocol, which then goes to the Twitch servers. Now the Twitch servers also have some protocol in here that gets you to the lab where I'm streaming from. It goes through the same streaming setup, and then up here you have OBS, and then we'll have Twitch here. So that's basically how this is working, right? And so you guys send requests to me, or rather, you guys send a request to Twitch. I am sending my data to Twitch through OBS. So yeah, this is a real world example. This is what's going on as we speak. That's pretty interesting, isn't it? Okay, so let's move on. So this is one of the reasons, let's see. I'll call Hassan and ask him to send me packets. Listen, that's a great plan, man. Sometimes you got to sometimes you got to tell him to get on the ball. Say, I need my content now. I need my engineering today. Okay. So note that the term protocol is used in two different ways. Well, isn't that confusing? So sometimes we're talking about abstract interfaces, and sometimes we're referring to the module that actually implements these two interfaces. Yeah, this is... You're listening to the NPR teaching stream by Engineering Today. Listen, I'll make you guys a promise. Do you guys want me to make you a promise? If the stream grows and continues to grow, we'll get the full NPR setup and we'll have nothing but NPR style ASMR teaching streams. That is the Engineering Today guaranteed to the Twitch and to the Streams chat. I guarantee it. Okay. So let's move on. So let's talk about encapsulation. So we're going over a lot of different types of protocols here, but like we said, this is more or less this is an introductory section, so we don't want to get too bogged down in trying to memorize every single protocol when we still have quite a few chapters before we get to them. So let's get to encapsulation. Okay, so consider what happens in figure 1.11. So 1.11 is where we drew this interesting graph, or we did this real world example of how my stream is getting to you right now. So consider what happens in... Okay, so we already went through this example, so we can actually completely skip over this because we came up with our own example. Okay, and so here we see a specific example for an application program. So an application has some kind of data. We have some request-reply protocol. Then we tack on the request-reply information on top of the data. This goes to the host-to-host protocol and gets tacked on. That way it knows how to communicate with another host. So this is the reply path that we're going through right now. Now we get to the host-to-host protocol. It decodes the first section of the message and makes sure it's in the right place. After it's in the right place, it then goes to the request-reply protocol and goes, okay, is this the reply to the request that I sent? Then it says yes. Then we only have the data, and then the data is what's given to the application program. Interesting. Very interesting. Okay. Let's continue on. So multiplexing and demultiplexing. So we talked about multiplexing a little bit earlier when we talked about links and channels and how we would multiplex them. So let's talk about it a little bit more. So practically speaking, this simply means that the header that the request-reply protocol attaches to its messages contains an identifier that records the application to which the message belongs. So that means that right here, when we decode this RRP, we have to know which program we're going to give the data to. That makes sense. So we call this demultiplexing key or a demux key. So we're going to have some key in the RRP that tells us who this data belongs to. Okay. So RRP is not unique in its support for multiplexing. Nearly every protocol implements this mechanism. So this makes sense. We can think about this intuitively. So generally, at every single stage, we want to make sure that we're giving our data or our current packet to the right person. So in this stage, when we're decoding the host-to-host protocol at this layer of the network, we want to make sure we're giving something to the right host. So we have to have some kind of key to decode that. Just like when we get to the request-reply protocol, we have to be able to make sure that we're giving the data associated with this partially decoded packet to the right application. Okay, so let's talk about something more specific. Let's talk about OSI, or the 7-layer model. So OSI, also known as the Open Systems Interconnection Architecture. So this is in figure 1.13. So we can see it's a little more complicated than what we've seen before. Defines a partitioning of network functionality into 7 layers, where one or more protocols implement the functionality assigned to a given layer. In this sense, the schematic given in figure 1.13 is not a protocol graph per se, but rather a reference model for a protocol graph. It is often referred to as a 7-layer model, and that's because we have application, presentation, session, transport, network, data link, and then we have physical. So we have 7 distinct reference points that we can design our network around. So what does the physical link do? So the physical layer, or not the physical link, the physical layer, it transmits raw bits over communication links. If we move one level up to the data link layer, this collects a stream of bits into a large aggregate called a frame. So here we have just bits. So maybe let's draw this out. So here we have bits, just 1, 0, 1, 0, 1, 1, 0, 1. In the data link layer, we have packets. So 1, 0, 1, 1, 1, 1. Okay? The network adapters, along with device drivers running in the node's operating system, typically implement the data link level. Okay. This means that frames, not raw bits, are actually delivered to hosts. So let's talk about the network layer. The network layer handles routing among nodes within a packet-switched network. So that means that these packets are sent to these switches or nodes, and they're routed accordingly. And so now these packets right here that we created, now these packets are going to be sent off in all directions. The lower 3 layers are implemented on all network nodes, so everyone needs this, including switches within the network, hosts to the exterior network, so everyone needs these 3 layers. Now let's talk about the transport layer. So the transport layer then implements what we have up to this point been calling process-to-process channel. Here, the unit of data exchange is commonly called a message rather than a packet or frame. Okay, so right here we have these packets going to certain places, and then before we send them to someplace together, we're going to regroup these packets, and they are going to tell us a story. They're going to be in a message. So there are less agreement about the definition of the top 3 layers. So these are more subjective, in part because they are not always present. So let's talk about the application layer. The application layer protocols include things like HTTP. So let's go ahead and write that down. So we can call this HTTP. Let's add an S here because most of the time we're using HTTPS. Hi, sorry, joined a bit late. Is this about analyzing communication between 2 computers? Yeah, so we're talking about network protocols in general. So this is this book is a computer networks book, and we're going to be talking about how we're going to design these overall networks. So in this case, we're talking about the OSI protocol, or the Open Systems Interconnection Architecture. Okay. So moving on. So like we said, it's HTTP in this layer as an example. Below that, the presentation layer is concerned with the format of data exchanged between peers. For example, whether it's integer, is it 16, 32, or 64 bits long, whether the most significant byte is transmitted first or last, or how a video stream is formatted. What allows HTTPS to hold that S moniker? I'm not too sure. That's a good question. So let me give it a quick Google. HTTP versus HTTPS. So hypertext transfer protocol. Okay, so here, let me pull up this image. Okay, so it's all about having an encrypted connection. So let me open up Chrome. So this is the difference between HTTP and HTTPS. The difference is that instead of having an insecure connection, we have some encrypted connection, and then we have some certificate on the other side. I'm guessing the certificate on the other side is what we use for decryption. And I'm guessing when we're talking about HTTP and they say 80 here versus 443, I'm guessing these are port numbers. So I think so this is the main difference between HTTP and HTTPS. Okay. Moving on. So right here, when we talk about the presentation layer, this is going to say, okay, so we're concerned about the Indianness, int, size, so those kinds of specifics. So the encryption aspect is the difference. Yeah, that seems to be the big change between the two. Other than that, it looks like they use a different port. So it looks like HTTP used port 80 versus HTTPS, which uses port 443. So the session layer provides the namespace that is used to tie together potentially different transport streams. For example, it might manage an audio stream and video stream that are being combined in a teleconferencing application. So then we have the session, which basically, so we can do, say, audio plus video. Okay, so let's go ahead and just run down how we think this may work. So we have HTTPS. We maybe send some request, or we're going to, say, do something over the internet. We check the sizes of everything. We want to see how we need to format our data. Then we combine our data as needed. So if we have audio and video, we combine those together into a set format. We put this into a message. Now the network takes this message as individual packets. The data link layer looks at these packets as these strings of bits in, say, a line. Then the physical layer only looks at the bits and transports them physically, where they go over to a physical layer of a network. It may go to the data link layer where they're formatted, and then at the network layer where they're put back into packets, and then they're sent to the end host, which again receives only bits. So sometimes they're just passed through. So physical layer to physical layer within this cloud environment. All right. Well, we got the OSI 7-layer model down. I just realized that I forgot a lot of the OSI model from when I last looked at it. Wow, that's incredible. So now that we've looked at the OSI model, it's important that we look at internet architecture. So this is usually called TCP/IP architecture, and so here we're concerned with the TCP/IP stack. So let's look at it in figure 1.14. So here we have FTP, which is, I think, the file transfer protocol, HTTP, which is this hypertext transfer protocol, I'm not sure what NV or TFTP are. So you may have heard of things like UDP servers. So let's go ahead and look at some background. So this all started with ARPANET, which was part of the Department of Defense. So this was the original internet. Okay, so while the 7-layer OSI model can, with some imagination, be applied to the internet, a 4-model layer is used instead. So in this 4-model layer, we have the application up here with below it, it can either be the TCP UDP layer, it could be IP, or some sub-network layer. So at the lowest level, we have a wide variety of network protocols, and so these are just called Net 1, Net 2, and so on. So these are all network protocols. So 802.11 may be one of the things down here. The second layer consists of a single protocol, so Internet Protocol. So everything is going through Internet Protocol. Then, the third layer contains 2 main protocols, either Transmission Control Protocol or User Datagram Protocol. So they're alternative logical channels to application programs. So TCP basically does a reliable byte stream channel, while UDP does an unreliable datagram delivery. So datagrams are messages. Okay, so we have 2 options here. So we have a reliable option and an unreliable. Now, it's not directly apparent to me why you would want one of each or why you would want the unreliable, but perhaps that'll become more apparent. So in the language of the internet, TCP and UDP are sometimes called end-to-end protocols, although it is equally correct to refer to them as transport protocols. So one of the things that's becoming apparent to me, because like I said, I'm learning this at the same time you guys are, it's becoming apparent to me that computer network engineers like to reuse the same terms over and over and over again when they're referring to different things. Interesting. You usually don't get architects doing that. Okay. So running above the transport layer is a range of application protocols such as HTTP, FTP, or Telnet, which is a remote login, or Simple Mail Transfer Protocol, so SMTP. So a lot of times if you've ever tried some scripting stuff with Python to automatically send an email, oftentimes SMTP is something that you'll probably have looked at. Contextual jargon. Yeah, listen, I hate contextual jargon. Avoid it whenever possible. Okay. So most people who work actively in the networking field are familiar with both OSI and internet architecture. Okay. So what are some features of internet that are worth highlighting? So that's best, just figure 1.15 shows this. So what's 1.15? Okay, so 1.15 is basically, basically the features that they want to highlight are TCP, UDP, IP, subnetwork, and then application. Okay. Seems to me they just like making things confusing. Yeah, it does to me. It does to me as well. I mean, they're giving multiple, in the same sentence, they're talking about protocol in 2 different fashions. They're defining these networks that are very flexible so that, or what's it called? So if you go back to the OSI model, they said that you do not necessarily need every single layer of the OSI model. It's interesting. I feel like in most other, or lack of inspiration, yeah, maybe they're just not inspired enough to, come up with different names, which is rather sad to me. Listen, one of the things that you'll find out is that architects love to come up with fun names for things. I actually was reading a security paper recently, and it made a reference to Hitchhiker's Guide to the Galaxy. It was the name of the paper, the title of the paper that got accepted into this conference was called So Long and Thanks for All the Bugs. So, which is of course in reference to So Long and Thanks for All the Fish from Hitchhiker's Guide to the Galaxy. And this got accepted into a conference. Okay. All right, so let's talk about implementing network software a bit. So we talked a lot about the hardware that it takes to get from point A to point B, but oftentimes it's just as important to talk about the software that will be doing this for us. So network architecture and protocol specifications are essential things. So of course we need architectures, of course we need protocols. But just as much we need a good blueprint, but a good blueprint is not enough to explain the phenomenal success of the internet. Just because we have a blueprint doesn't mean why does this work so well. So what explains the success of the internet? So there's many factors. So a good architecture, new functionality, and then another related factor is the massive increase in computing power. So this is where people like, I hate when I say this, but this is where people that are in my field, like myself, come in. So architects and device engineers are the people that really have driven a lot of these fields because we've made computers sufficiently powerful enough to do these complicated tasks. Okay. Let's see. So I think we can go ahead and skip the rest of this because I think they're just talking about a historical perspective. So let's talk a little bit about application programming interface. So actually talking with sockets. Okay. So when we refer to the interface exported by network, we're typically referring to the interface that the operating system provides, and oftentimes the interface that the operating system will provide is something called an application programming interface or an API. So we'll use the API to do these low-level calls. If you're doing your PhD, does that mean you're currently doing a research project? Yeah, I'm actually involved on a couple of research projects. I'm doing some very interesting stuff right now. I have a conference deadline in August. I'm submitting a paper to that conference, and I'm also co-authoring a paper going to another conference that is due around that same time. I'm trying to write a research paper that will that will go to a conference that's a month or two after that, and then another one at the end of the year, hopefully. Okay, so although each operating system is free to define its own network API, over time, certain of these APIs have become widely supported. Have you ever submitted to IEEE conferences? Yeah, that's like the only conferences that I submit to. So, there's a conference called ISPAS, which is the IEEE International Symposium on Performance Analysis of Systems and Software. There is ISWIC, which is the International Symposium, it's the IEEE International Symposium on Performance Analysis of Systems and Software. There is ISWIC, which is the IEEE International Symposium on Workload Characterization. And then there's other conferences such as the more relevant ones to me, which would be the HPCA, the IEEE Conference on High Performance Computer Architecture. There's ISCA, which is the International Symposium on Computer Architecture. And then there's Micro, and then there's Sigmetrics, but I think pretty much all of these are related to IEEE. I don't think any of these are really separate from IEEE. Okay. any other questions about my research or what I currently do. So here, the one of the fun facts right now is that I'm actually streaming from my lab. Oh yeah, and when you said that I was busy, I am absolutely busy. Yeah, I have a lot of irons in the fire, but it's a lot of fun. I enjoy what I do. See ya, gotta go get dinner. Hey, have a great night, man. Thanks for stopping by, Kamikaze Chicken. Good place to start, even for undergrad. Oh wait, I must have missed a message. Whoops. Yeah, so, I think that doing research is a very interesting thing because research is a fundamentally different problem than coursework. So when you're doing research, you really have to think outside the box because when you're doing coursework, all of your problems have already been solved. They're problems out of a textbook. So, that's one of the big reasons why I like research is because it's fundamentally a very different problem. Okay, so let's continue on with what we're learning about computer networks. Okay. So, before describing the socket interface, it is important to keep concerns separate, or it's important to provide a certain set of services, let's start over. We started really poorly there. Okay. So, before describing the socket interface, and so what's a socket interface? Right here. This is what happened with the socket interface originally provided by the Berkeley distribution of Unix, which is now supported on pretty much everywhere. So when we're referring to APIs, that's also what we're referring to when we're talking about these socket interfaces. So before describing the socket interface, it is important to keep two concerns separate in your mind. So one, each protocol provides a certain set of services, and the API provides syntax by which those services can be invoked on a particular computer system. The implementation is then responsible for mapping the tangible set of operations and objects defined by the API onto the services. So there has to be some kind of mapping of operations to services. However, we want programming to be easy enough where we can have generality. Oh, that's you? That's why you thanked me for the follow. I was confused because I never remembered following a stream named Why So Green. Yeah, it's me. I'm the one that does the computer engineering streams. Okay. Okay. So the main abstraction of the socket interface, not surprisingly, is something called a socket. Well, isn't that grand? Our interface that we call the socket interface deals with sockets. So a good way to think of the socket is a point where a local application process attaches to the network. So it's an attachment point to the network. So the interface defines operations for creating a socket, attaching the socket to the network, sending and receiving messages through the socket, and closing the socket. So we have a very nice set of operations we can do with something like a socket. So how do we first create a socket? So usually we can do something like int socket, and then so it's this function right here. So that it's going to return an int, which will either be a success or a failure. We need to give it a domain that we're trying to attach to or connect to, a type of socket, and then also the protocol that we're going to be talking with. So like we said, the domain argument specifies a protocol family that is going to be used. So PF INET denotes the internet family. Unix denotes the Unix pipe facility. Packet or PF packet denotes the direct access to the network interface. So actually bypassing the TCP/IP protocol. So that's very interesting. So the type argument indicates the semantics of the communication. So sock stream is used to denote a byte stream. So we're communicating these set of 8 bits every single time. We have dgram, which is a message-oriented services, or message-oriented service. So this is going to be from UDP. So like we talked about earlier, UDP sends messages, while TCP sends, I think it said bytes. In our case, this argument is unspec, which I think just is unspecified, because the combination of PF INET and sockstream implies TCP. So we have some implicit declaration here. And then we get a handle of the socket. Okay, so this int is actually a handle. So this is how we're going to refer to the socket. Whatever we assign to the socket will be on the left side of this function. Okay. And then we have, of course this depends on the kind of socket we open, but we have other functions such as bind and listen and accept. So this is reading and accepting. So let's go ahead and start. So bind, we attach the socket to a specific address. Listen defines how many connections can be pending on the socket. And then accept carries out the passive open. So what was passive open? Let's see. Okay, so passive open is when the server says that it is prepared to accept connections, but it does not actually establish the connection. Okay. So accept is basically saying that it can accept the connection now. Okay. And then we actually have something that says, go ahead and connect now. We have more functions to do, sends and receives. And all of these things are something that we can interface with using a low-level language like C. So then they go over an example application. And so what you need to do if you're trying to do some C programming and do some socket programming, you need to include, the sys socket header file, the inet header file. I'm not sure what netdb is. They make some defines appear on, so this will just be a port number that they're trying to create or connect to. And so basically they just implement a simple socket program. So we can skip over most of this. A brief note on performance. So this is basically just saying that the first thing we want to do is focus on getting the data correct, and then we'll make it go quickly. So fundamentally different than computer architecture. So computer architecture, it seems a lot of times that we create something that goes extremely fast, and then we patch up all of the issues with it later on. Okay, then we have a note on bandwidth and latency. So bandwidth or throughput and latency, sometimes called delay. I've never heard it called delay. And that's how we characterize network bandwidth. Okay. So while you can talk about bandwidth of networks as a whole, sometimes you want to be more precise, focusing, for example, on the bandwidth of a single physical link or of a logical process-to-process channel. At the physical layer, bandwidth is constantly improving with no end in sight. So this is saying that when we're getting to the architecture layer, so at my level of work, because I'm a computer architect, that there doesn't seem to be any slowdown in what people in my field are doing improvement-wise. Okay. So the more sophisticated the transmitting and receiving technology, the narrower each bit can become, and thus the higher bandwidth. For logical process-to-process channels, bandwidth is also influenced by other factors, including how many times the software that implements the channel has to handle and possibly transform each bit of data. So the number of operations that we're going to be working with is going to affect our latency and affect our delay. Okay. And so this is just a note on latency. So if we have a faster clock cycle, clearly we're going to be processing things faster because the distance between, if we have the same overall architecture, then we should be processing things twice as fast if we have a transmission rate that's twice as fast. So 1 megabit per second versus 2 megabits per second. Okay. So the other performance metric, latency, we often classify as something called RTT, or round trip time. So this is the time it takes for me to send something across the network and then receive something back. So a lot of times, if you just open up a shell and you do ping google.com, what you will get is the round trip time of each packet. So when we talk about latency, it has 3 components. So there's the propagation delay. So this is the speed that it takes to send something over a wire. So if you know the distance, physical distance between 2 points, you can calculate the actual propagation delay. They're doing a pretty reduced example, so they say that it can go as fast as the speed of light. Usually you get to like 1/3 the speed of light or 2/3 the speed of light, which is still pretty quick, but it's not quite the speed of light. Ideally, it would be the speed of light. Okay. So second, there's the amount of time it takes to transmit a unit of data. And so this depends on the size of the packet you're transmitting. And then there are queuing delays inside the network. And so this is basically how quickly you can get through all the different nodes to get from end to end. So latency is going to be propagation plus transmit plus queue. Propagation delay is just the distance over the speed of light, and then our transmit is just going to be size over our throughput or bandwidth. Okay. So if we move a little bit forward, let's see. So here we're just doing a couple examples of calculating round trip delay or round trip time, and also looking at bandwidth examples. But these are fairly simple, so we'll leave these to, maybe a problem-solving session. Okay. And so here we have a perceived latency versus a round trip time. Okay. Now let's look at the delay bandwidth product. So it's useful to talk about the product of these two metrics. So this basically just says if we multiply the delay by the bandwidth, this can be another kind of metric that is useful to design a network around. And so if we think of this as a pipe, the bandwidth is basically the diameter of the pipe, how much we can shove through it per little, say delta length. So our throughput is here. It's the area here, while the delay, we'll call this tau, is how long it takes to send one slice of data like this all the way across the network. Okay. So this is the delay bandwidth product. So now we get a little bit of context into the size of networks. So, when we're talking about, back in the day, in the 90s, when we're talking about dial-up, or even early 2000s. So we're talking about a system that has around 56 kilobits per second, that has a one-way distance of around 10 kilometers. It has about an 87 microsecond round-trip delay time, and then a round-trip time bandwidth product of 5 bits. This is pretty small. This is pretty small. So then we go on to something a little bit faster. So something like a wireless LAN. We can get a much larger bandwidth now than dial-up. So instead of going over those little dial-up cables, we're now going over some wireless network. And we get an order of magnitude increase in bandwidth. We get a much farther one-way distance, so 50 miles instead of 10 kilometers. Now, you can hear the dial tones in my head right now. Yeah, listen, I remember back in the day signing on to AOL. That's a sound that's burned into my head, and I will remember forever. Okay, so let's talk about high-speed networks. So then we get to satellite, which, we have, it's a little bit lighter on the bandwidth side, but we have a much, much farther distance. We have a much, much longer round-trip delay time. However, with this metric, we get 10 megabits. So if we're only looking by this bandwidth delay product, it seems like satellite is, suddenly really, really far in the lead, even though, in actuality, it's much slower in our round-trip delay time. It just happens to have a very, very far one-way distance. Okay. And then, of course, we have cross-country fiber. So this is a fiber optic connection. So this is traveling at roughly the speed of light. So very high bandwidth, 10 gigabits per second. So another order of magnitude, or a little bit less than an order of magnitude increase over satellite and wireless LAN. It has a modest distance of 4K, or of 4,000 kilometers. And then it has, it's slower by, a fair chunk. It's about 100 times slower than a wireless LAN. However, it's about 6 times faster than satellite. So, it's a little bit of a trade-off. And so we have, the best compromise here, at least as far as this round-trip time bandwidth product. Okay. So let's continue on. Okay, so this is just going over what we've kind of talked about. Here we have the relationship between bandwidth and latency. So a 1 megabyte file would fill up the 1 megabyte per second link 80 times. So if we have this 1 megabyte per second cross-country link, then we would need to serially transmit 80 of these pipes over this link. However, if we had some giant 1 gigabyte per second cross-country link, we could just send, maybe 1/12 of this pipe filled with this data. So we could potentially put 12 times as much data at this pipe. And so this is a really interesting design when we're talking about companies like AT&T, and when they're designing a network. They need to run tests to kind of say, well, what are our users doing? Do our users need maybe this smaller pipe that's very, very fast? Or maybe do they need this high throughput pipe, and we can get a bunch of users that maybe they care less about latency, but they have a lot of things to send. Okay, some more metrics. So calculating throughput and transfer time. Then we have a little note on application performance needs. So the discussion in this section has taken a network-centric view of performance. That is, we have talked in terms of what a given link or channel will support. The unstated assumption has been that application programs have simple needs. They want as much bandwidth as the network can provide. This is recently true of the aforementioned digital library program that is retrieving a 25 megabyte image. The more bandwidth that is available, the faster that it can return with the image. If we could transmit 25 megabytes in a single go, that's great for us. So, however, some applications are able to state the upper limit on how much bandwidth they need. So video applications are prime examples. It says, okay, well, if I'm a video, I'm going to be transmitting at, say, some set resolution. So I know exactly how much bandwidth that I will need. But unfortunately, not every single application can give you that kind of information ahead of time. So, and here they're talking about even for videos, because the difference between any two adjacent frames in a video stream is often small, it is possible to compress the video by transmitting only the frames between adjacent frames. Each frame can also be compressed because not all the detail in the picture is readily perceived by the human eye. The compressed video does not flow at a constant rate, but varies with time according to factors such as the amount of action and detail in the picture and the compression algorithm being used. So this says that oftentimes we can play some tricks with the network. That way, if say we have two pictures, and let's say 99% of the pictures are the same, and there's only a 1% difference. Well, to completely send a new part or a new picture, well, that would be a little bit naive, because then, the information difference between these two frames is very small. So they're saying that we can use something like compression in order to, kind of limit the data we're sending. But at the same time, it makes our network non-constant. So generally, however, it is possible to put an upper bound on how large a burst of an application like this is likely to transmit. So you can do some profiling of applications and very specific lab-like scenarios, but also in something as common as real-world scenarios. You can do some real-world profiling and try to find an upper bound, and then put a little bit of padding between the upper bound and what you can actually support in order to handle maybe all possible cases. Because you have to remember when you're an engineer or when you're an architect, you have to say at some point, I can't support everything. I have to cap support at a certain spot, or else I'm going to be making modifications forever. You have to eventually say, this is good enough for what I need. Okay. So then there's something called jitter, which is a variance of latency. So that's something that I think we can all kind of understand. So yeah, pragmatism. Pragmatism is something very important in research. So not only in research do we need to say, well, what can we make better? At some point we have to say, well, what's useful to make better? Okay, so let's move forward a little bit. Okay, so this is what we were kind of saying earlier. So we may be giving our packets from some source to a network with a consistent inter-packet gap. However, because networks have a non-deterministic nature to them, we don't know how everybody is using the network. We may have, Bob, Sue, and Amy all sending packets as well at the same time. However, in another scenario, maybe nobody's sending packets. Maybe you're somebody that has exclusive access to a network. And this is going to determine how this interpacket gap is going to change from our packet source to our packet sink. So our packet sink is just our destination. We can think of this as just a destination. To understand the relevance of jitter, suppose that the packets being transmitted contain video frames. So when we're playing something like a video, we really want, a consistent viewing experience. We don't want to have 5 frames a second, then 144 frames a second, then 60 frames a second, then 24 frames a second. We want something like always 24 frames a second or always 60 frames a second. Downloading torrents all day. Yeah, I mean, that is an example. That is an example. I don't particularly torrent. However, it is an example of computer networks in action. If a frame arrives early, then it can simply be saved by the receiver until the time to display it. But let's talk about the more important scenario of late frame arrivals. So then we will have the video quality suffer and not be smooth because we're waiting on data. We cannot proceed until we get that data. And so this is where that idea of QoS, or quality of service, comes in. We need to make sure that we're providing, if you're a video streaming company, you have to have certain quality of service goals. You have to say, we don't want our users seeing videos below 24 frames a second or 30 frames a second. So they have a goal that whenever they're sending something, that it should arrive in the time that can support that. And so they have to tell network architects something like this so they can design the network accordingly. So let's talk about a summary. Let's just summarize what we've gone over in this chapter. So first of all, the internet has experienced enormous growth since it started and over the past 30 years, since the days of DARPANET. So much of this growth is because of the general purpose nature of computer networks. They can be used for many different things and many different tasks. So the first step to becoming a network architect is we have to carefully identify exactly what we expect from the network. So we have something we want to do, we have to be able to put that down on paper so that we can explain it properly. So cost effective, scalability, our connectivity, these are all things that we need to be able to specify ahead of time. We also need to define a layered architecture that will be the blueprint of our design. So we need to define some set ways that we're going to be talking from point A to point B. And so we talked about this with things like the 7-layer OSI architecture and the internet architecture. And so we're mainly going to be following the internet architecture. So the third step is, how do we implement networks, protocols, and application programs, usually in software? So we need protocols and applications to interface and invoke the services of other protocols in the network subsystem. And so when we're usually talking about this, generally we're referring to sockets. So finally, what is the last thing that we require in order to be network architects? So when we're designing a network, the network as a whole must offer high performance, where the two performance metrics we're interested in are latency and throughput. So the last thing we need to be concerned about when we're designing these networks to determine the validity of the worth or the value of our network is A, do we get things from point A to point B in a sufficient amount of time? And B, how much information did we get from point A to point B? And so these can be combined in something called a delay bandwidth product. And so this provides a critical role in something like protocol design. Okay? So it's apparent that, okay, so that's basically the summary. So then we have a couple closing thoughts. So basically, it's apparent that computer networks have become an integral part of our everyday lives. And so, we're talking about 40 years ago when ARPANET came around. We've come a long way from ARPANET. But the difference between ARPANET nowadays is that, the internet has become a business. So places like AT&T and Comcast, so it said that there's a lot of players out there, but there's actually not that many anymore. Is throughput determination something that can always be adjusted once the first two steps are completed? Somewhat. Not all the time. A lot of times throughput depends on the technology you're using. So a lot of times throughput is determined by the kinds of cables you're using. So the kinds of fiber optic cables are rated for different throughputs. So that's usually infrastructure improvements. You can't, say, do a software patch that improves throughput. That's usually hardware. Okay. And, an increasing amount of services require on using networks. So VoIP, voice over IP, so things like Skype, online games. Online games is actually a very interesting thing. So a lot of times, what happens with online games is that a lot of the graphics rendering is offloaded onto the cloud. And so we really, really, really care about latency in these situations because we need to render the frames in the cloud, and then we need to send that data back to individual host machines. So what's next? Cloud computing. So I'm not sure how old this book is, but cloud computing is one of the very hot topics nowadays. So Amazon is one of the big players in cloud computing with something called Amazon EC2, which stands for Amazon Elastic Compute. And so that's basically, you can buy compute time on these servers in the cloud. And then they have a section on further reading if you want to learn more about computer networks. Okay. Very, very interesting stuff. Okay, so then they have some exercises at the end of the book. We can skip over that for now. And let's see what we're going to learn next week on Wednesday when we talk about computer networks. So next time, we're going to talk about getting connected. And what does getting connected include? Getting connected is going to include, let's see, where is the table of contents? Oh, they've got a foreword by David Clark. Interesting. Okay, so chapter 2. We're going to talk about the many different ways that a user can get connected to a larger network, such as the internet. So we're going to introduce the concept of links in more detail. We're going to describe many issues at the link level of protocols. And this is going to be encoding, framing, and error detection. So error detection a lot of times has to be done, or most of the error detection has to be done at this level, because it's at this level we have things like many bits in a row, and we need to make sure that this 0 isn't supposed to be a 1. We need to be able to take these bits and format them into their own respective data frames. And then we need to figure out how to communicate them someplace else. Okay, so that's about all we have in regards to computer networks for today. We still have some time left. We have about 20 minutes. So I'm going to leave this open to any kinds of questions, or if anybody has any questions about any topic, or if they want to look at something in particular, we can do that now. I'll go ahead and pull up the paper that I'm reading recently. So I'm reading this paper right now. It's from 2017. It's on the efficient exception handling support for GPUs. Let me see what conference this was in. This was from 2017. I forgot the specific conference. It was at, let's see. Here's something funny. So in that chapter, we talked about the Association for Computing Machinery. So I'm actually getting this paper from the ACM Digital Library. So the example that they use in that book is actually what I use to find these papers. So this was actually at Micro 50. Okay. So this was in Cambridge, Massachusetts last October. Okay. Interesting. What source do I use to acquire my textbooks? So I actually get them through the university. I get them through my lab and from my professor. And also any recommendations for applications that I can use to view and highlight texts in Windows OS. Okay, so if you want to do this in Windows, your best bet is to use something like OneNote. OneNote is an amazing program for doing exactly this. There's a better program. I forgot exactly what it's called. It comes preloaded if you have a Surface Pro tablet, but it's a PDF markup app. Here, we can actually look it up together. So, Windows PDF drawing, Windows Drawing PDF. Is it called Drawboard PDF? Is it this one? Okay. So, no. So it's Drawboard PDF. It's $10, and this is a really, really good app for drawing on PDFs in Windows. You do have to buy it. So I use Linux, of course. So I use it's Journal, but instead of a J, it's an X. So it's Xernal. I don't know how you would pronounce it if you're trying to say it. So I use this app. Like I said, it's called Xournal. But yeah, so if you use something like OneNote, you can do it in OneNote. Otherwise, you could do it in that PDF Drawboard app. But then you have to pay $10. But I suppose if you're using OneNote, then you would have to have Microsoft Office. Okay, you were researching it, but I can't use it on Windows 10. Listen, you can't use this on Windows 10 or Windows period, but guess what? This is the best application for drawing on Ubuntu. This application is so much worse than something like OneNote or something like that journal editor, the journal whiteboard. This app is so much worse than those. You know, this just happens to be the only one that's decent on Linux. Linux does not do a great job at supporting drawing tablets. Or rather, the drawing tablets don't do any of the support for their software. They don't do any of the support for their software for non-Windows, non-Mac operating systems. So I use a Wacom or a Wacom Intuos Art drawing tablet to do all my drawing, and it was a pain and a half to get it working on Ubuntu, and I'm still having problems with it, which is the reason why my drawings sometimes look like a kindergartner. Now, I'm not terribly happy with the way things are currently set up. I want to eventually have a dedicated streaming PC that's not my lab machine, so I don't have to stay in my lab to do in order to do these reviews. But hey, that's a dream for the future, right? Yeah, so this is an interesting paper. So this is a follow-up from a 2012 paper. I use OneNote regularly for journaling, so I'll see what I can do with PDFs using it. Yeah, so what you have to do, there's like an insert on one of the tabs, and on insert, first comes the webcam drive, and then streaming PC donation drive, Abather. Yeah, so the webcam drive is first, of course. I mean, we were only getting like 13 viewers per stream, so, you know, I'm not getting too hopeful about, donations or something right now, but listen, that's okay. When I get paid out of my fellowship at the end of the month, I'll pick up a webcam, but I'm not going to put any money towards a streaming PC. I just need one Hajri. Yeah, maybe. How many computer classes do you think I have to take for mechanical engineering? I know I have to take some code classes, but I don't know. So that depends university to university, Phenom. So most of the time as a mechanical engineer, you have to take an intro circuits class. You have to take an introductory programming class. I would guess you might have to take something like a mechatronics class, which is how you would use something like microcontrollers to integrate some action between some mechanical objects, so maybe like building a robot. And so working with servos to control, or controlling some servos to do a specific task and making some kind of robot. You generally don't need too many computer classes as a mechanical engineer. Now, of course, the more knowledge you have on computers or computer engineering can be beneficial for you, but it really depends on what you want to get into. You took a programming and cumulative electrical and computer engineering class as a mechanical engineer. Yeah, so I was actually a mechanical engineer. When I was in undergrad, I started out as a mechanical engineer. That was freshman, sophomore year, respectively. Yeah, I did the exact same thing. Basically, all freshmen have to take the same classes. So if you're a freshman electrical engineer, you have to take the same classes generally as a mechanical engineer. Cool, yeah, I know robots are really big in this major. Yeah, so so the most you probably need to know about computer engineering is really some low-level programming, so how to program a microcontroller, how to program something like an Arduino, and how to directly interface and read spec sheets of those devices, and how to integrate hardware to do what you want with software and that microcontroller in the middle. But all my Mech lab projects involve some level of programming or circuitry understanding. Yeah, absolutely. See, that's one of the big problems, is that people think that if you don't have a solid foundation of electrical engineering, then oftentimes you make really, really silly mistakes if you're a mechanical engineer trying to implement something physically. So things as simple as not looking at the electrical ratings of components, or things like not understanding that some amplifier has a limit to its current output, and that's why your thing's not broken. You don't have a broken component, you're just not generating enough current. Another big thing that a lot of times mechanical engineers tend to overlook is voltage ripple. So they don't understand that sometimes you need to just add some capacitors to your circuits in order to smooth out your power rails. And so, there's all these little subtle details that can be really useful information if you're a mechanical engineer from the electrical engineering side of things. Oh, we got another follower. K Finch 3420. See, it's really funny right now. So I don't know who following me has actually visited the stream yet, because I posted on 4 different subreddits an advertisement saying I was doing some engineering streams. However, this was going to be an interesting test to see what the conversion rate of the 100 or so extra follows I got on Twitch, how that translated to views on Twitch. So I'm going to look at the data after this, and I'm going to see. Oh yeah, I saw you on Reddit. Well, hey Phenom, thanks for stopping by. I appreciate it. Landy, you did as well. Hey, thank you for stopping by. I appreciate you. K Finch saw my post on Reddit. Hey, look, we got 3 out of 100, and I'll be able to see the number of unique people that have visited the stream. So I'll try to see if I can cross-list that with people that were in chat at some point, and then that way I can get a better idea of of things like conversion rates. I think that would be some interesting statistics to try and plot. I was too scared to jump into an ECE minor at my school, so I've been learning the material on a personal level. But these lectures draw me closer to the dark side. Phenom, is this the first stream? Nope, this is actually I don't know, this might be the 10th or the 11th stream. So if you go on my YouTube channel, there's a link to it below. I have all the previously recorded streams on there. So I've done, let's see, I've done 4 streams on computer architecture. Freizig, the stream has gotten me stressed again, and I only finished exams yesterday. Hey man, listen. Freizig, we don't need to be stressed on this stream. This is fun learning. I'm having a good time learning this. I know some other people that aren't even computer engineers are having a fun time, learning something new. This is all about fun. Oh, Landy, you did exams too? What did you guys have, like a Maymester class or something, or did you just have like a summer class, or do you just have exams this late, or is this still the spring term for you guys? Oh, you're in Australia? Okay. So it's different. Okay. Sure. Okay, yeah. I'm in the US, so we're in the summer term here. And so, well, we're in the summer term here, but I basically just do research during the summer. Yeah. So what was I talking about? I was talking about, okay, so Versuch was saying you were too scared to jump in EC as a minor, but you're being tempted close to the dark side by this. Listen, it's all about just finding the specific thing that you want to do. So if you can take some of the content from these streams and apply it to your interests, that's good enough. I think a lot of times the big problem that people have is that they think that they should get multiple undergrad majors or minors, and that's not necessarily a good thing unless it has direct relation to the job you want. So let's say if I got a double major in mechanical engineering and electrical engineering, I would go to apply for a PhD in computer engineering, like I did, and nobody would care that I have a degree in mechanical engineering as well. Nobody would care because, the architecture that I do now, nobody cares in computer engineering that I knew about structural dynamics. No one cares about, vibration type analysis. They're not going to care as an architect. They just care about my architecture knowledge. So it's important to kind of hone in on what you want to do. And, at some point you've got to put the blinders on a little bit. At some point you have to narrow in on your specific task. And you have to say, okay, all these other things are interesting, but do I really want to put myself through all the stress of a class that I may never use again? And so sometimes the answer is yes. Sometimes you really do want to put yourself through that stress because, it's just a fun experience and it's something that you want to do. But it's important to be realistic about some of those things. Okay. We have any other questions? So, you guys that are in chat, is there any other kind of content that you guys are looking forward to? So I have the outline of the content that we're going to be going over below in the what's it called? The schedule. However, I'm open to changing some things up. I know Saturdays I have kind of a free block where it's undecided what I'm going to be streaming, so we have some flexibility there. Saturdays we're doing something completely different. We're learning German and Japanese, so that's fun. I like today's stream because we are learning at the same pace. Oh, very nice. So that should be the same for today's stream as well. The streams on Wednesdays and the streams on Tuesdays should be very much like that, because this is my time taking a course first time taking a course in compilers as well as a course in computer networks. So we're kind of learning this both together. I understand these from a conceptual point of view, but in a lot of ways my knowledge of it is fairly limited. Okay. I think I should probably do some math streams as well. I might spend some time tonight doing some math on stream. I'll probably take a little bit of a break, walk around, maybe get some coffee or something. It's already 10 p.m. here, or where I live, so I might take a little bit of a break, like a 20-30 minute break, but I think we might come back and I might open a linear algebra book, and then we can just maybe go through the first chapter of a linear algebra book. That might be interesting, and that's just a bonus stream that I think we might do tonight, or we might do it very early tomorrow morning. Dang, I'm in calc right now? Hey, nice. So when I was in undergrad, the math classes that I had to take Calculus 1, Calculus 2, Calculus 3, linear algebra and differential equations. I had to take partial differential equations, and I had to take probability and analysis. Those were the math classes that I had to take when I was in undergrad engineering. Is that the same everywhere? Does everyone have to take that? Yeah, so the class that I took was called linear algebra and differential equations. Yeah, I know what you mean. Yes, I think I have the same as you. Okay, so that is common everywhere. See, it's a funny thing that now I'm a computer engineer, because the kinds of math classes that I actually would like to have, I didn't take as an undergrad. Like, right now, I don't even know if I will ever use much of calculus ever again. However, well, no, that's not true. So I'll use it applied in other scenarios. Like, it's very unlikely that I'll use something like differential equations again, or I'll never use partial differential equations again. But the things that I really wish that I would have been able to take in undergrad is graph theory and set theory. I really, really, really wish I would have been able to take a class on queuing theory. That would have been really, really useful to me, because if you think about computers are basically just a bunch of queues. Whereas such, I only now realize that my favorite way to learn things is from a historical perspective. So I've been relearning a lot of stuff like that. I think that's a great idea. Listen, that is an amazing idea. That's why I love architecture so much, because architecture, you generally learn it from a historical point of view. So that's why one of the first videos that I posted on YouTube was on EDVAC, the first stored program computer from 19. It's a paper from 1945. EDVAC was designed and built between 1944 and 1946. Phenom. I wanted to be a chemical engineer, and we only had to take up to Cal 2. Yeah, that's the thing. And you just don't need it in some fields. It's just wasted time learning it. I hate saying wasted time, but you don't get a ton of benefit out of it in some fields. But listen, I hate organic chemistry. I hate it. I have a friend that's doing I have a friend that loves organic chemistry, and he's getting a chemistry PhD at, I think, Princeton or Yale. And I just don't understand it. I told him he was making a terrible decision. I told him to reconsider. I have to get special hexagonal graph paper for that? Yeah, unless you want to draw a billion hexagons by hand. Listen, that's why engineering paper is the best. You get that yellowish engineering paper, that's number one. Oh, what is it? The manila engineering paper? The green one's terrible. The green one is low quality and you don't want it. You've got to get the one that's yellowish. Alright guys, well, thank you for stopping by. Make sure to tell your friends about the stream. If you enjoyed the stream, give it a follow if you haven't already. We've got the links to the YouTube and Twitter down below if you want to give me a follow there. I'd be happy to talk with you on those platforms as well. Listen, always reach out to me if you have any questions, you have any concerns, or hey, even if you just want to talk, or maybe you have a suggestion for content that would be good for the stream, I'd be happy to listen to it. Until tomorrow, guys, I'm Engineering Today, and I hope you learned something. Thanks for stopping by.